Hello, students. I'm your physics tutor, Professor Jitesh Jain from mytutorsonline.org. Right? Okay. Today we are going to study the Huygens wave theory. That's a very important theory of physics. This is the part of the wave optics, dear students, and one of the very important questions related to the board exams are being asked on this theory. That is the Huygens wave theory. Right? Okay, so let's start the Huygens wave theory, students. It's a very important one for the board exams, particularly, right? So, firstly, I will share my screen for this to you. Let me just, okay. So, students, I will share my screen with you, right? All right. So, let's start the Huygens wave theory, right? Huygens wave theory, right? See, this theory is basically aims at one very important thing feature in physics, and that is known as what? The propagation of the light waves, right? Propagation of light waves. That means how do the light waves propagate? Okay, that particular principle was explained by Huygens in the form of his wave theory. So that is why it is known as the Huygens wave theory. So first and foremost, we had to learn the concept, okay, of the wavefront, dear student. This is the concept when given by the Huygens wave front. Okay. If we consider the light of a wave nature, suppose, then the source of light is there. Suppose this is a single source of light. Then across the source of light, there will be several particles which is going to vibrate, okay, together in the same phase, right? Okay, these particles are going to vibrate in the same phase. So the locus of all these particles which are vibrating in the same phase, right? Okay, that means the locus of these particles, locus means what? The moving point in maths, right? So locus of all these particles which are vibrating in the same phase, this is known as what? Wavefront, dear students, right? Okay, so what is wavefront? Locus of the points, right, which are vibrating in the same phase, which are vibrating in the same phase, right? So this locus is of these points which are vibrating in the same phase are known as wavefront, and these points are particularly known as what, dear students? These are known as wavelets. We call wavelet as a single source of light is, and when all these sources of light you join together, it forms some locus, right, or some shape, and that shape is known as what? Wavefront. For example, the shape which is formed now, this is basically what here, this one is a point source of light. Okay, so when the locus of all the point sources of light are joined together which are vibrating in the same phase will form what? This will form the spherical wavefront. Okay, this is basically what? The spherical wavefront. All right. Now, students, okay, when I'm saying the spherical wavefront here, okay, what does it mean basically? Right, it means that the wavefront will be in the shape of the sphere. So, owing to that, okay, there are basically three kinds of wavefront, dear students. Okay, so what are the three kinds of wavefront, dear students? Let us see that. Okay, let us observe that three kinds of wavefront, which are very very important to understand. Right. So let us see all these three wavefronts now. The first wavefront will be what? The spherical wavefront. Okay. right? For spherical wavefront, you need a point source of light. This is a point source of light. Okay. And when the locus of the particles which are vibrating in the same phase in the point source of light, it will form a spherical wavefront. Next one is what? The cylindrical wavefront. Cylindrical wavefront. So what is a cylindrical wavefront, dear students? That when the source of light is linear to us, okay, when there is a linear source of light, that means the source of light will be linear. Let's say this is a linear source of light. Okay. Then what is going to happen with the linear source of light? What is going to happen? The vibration of the particles will going to happen around it like this, right? Okay. So this will form what? This will form a cylindrical wavefront, dear students. Okay. This will form a cylindrical wavefront. So what is a cylindrical wavefront? How does this form? When source of light, okay, is linear, it forms cylindrical wavefront. All right, very simple. Right now, the next one is what? After this, if suppose this linear source of light same is seen from a very far distance, right? It will form what? It will form a planar wavefront. How the planar wavefront is formed? That if you are seeing this linear source of light from a very far distance, let's say, then this will be seen as what? A kind of a wavefront which is known as what? The planar wavefront. This will be a planar wavefront. That means you are not going to see the three-dimensional shape of this. You are going to see the two-dimensional shape of this, right? 2D shape of this. So that is why this is known as what? This is known as the planar wavefront, dear students. Okay, when cylindrical wavefront is seen from a very far distance, or you can say the linear source of light is seen from a very, very far distance, then you can say it is basically what? It is the planar wavefront, dear students, right? Okay, so now we will continue with our theory again, right? Next is what? After this, there are two important things which are very, very important. Okay. Okay. So now the next one is what, everybody, which is very, very important is what? Okay. So the next theory is what? After about the propagation of the light, the Huygens wave theory. Firstly, introduce the concept of the wavefront, as you can see here, as I explained you, the concept of the wavefronts, right? Okay, but the next one is what? After that, the theory of wavefront is given. Then he explained the propagation of light. How do you explain this, the propagation of light? Let us see that using the theory of the wavefront itself. I'm going to show you the basic idea of the propagation of the light. So let's start the basics of the Huygens wave theory. So he has taken two concepts. One was the wavelet, right? Wavelet theory, and that is what wavelets are of two types. One is the primary wavelet, right? Primary wavelet, and the other one is known as what? Secondary wavelet. Okay. When you are saying primary wavelet, that means what? This will be the source of light, primary source of light. Okay, primary or the initial source of light. Okay. So what is his theory? As per the theory of these wavelets and the wavefront, what he says that each point source of light, okay, that is wavelets, that is primary wavelets, right? Wavelets in the given wavefront, in the given wavefront will be formed by these primary wavelets itself, will act as a source of what? Secondary wavelet. That means the primary wavelet will form the replica of the secondary wavelet, and so on the light is propagating. So let us understand this concept, this theory, which is explained by him by using the diagrammatic representations, dear students. Right? So how do we do it using the diagrammatic representation? Let us see that. So first and foremost, the primary wavelet I will draw. Let us see that. Let us suppose that this is a cylindrical source of light. Okay, so there are number of wavelets here. This is the one wavelet. Around it, this is a point size wavelength S1. Then there is one more wavelet here, point size. This is S2. Then there is one more wavelet here. Okay, point size. This is S3. And there is one more, the point size, that is basically what? S4. So as per the Huygens, what is going to happen? This will be what? These are the primary wavelets. These are what? These are the primary wavelets, dear students. So this primary wavelength is going to replace now itself with the secondary. That means it will form the secondary wavelet. That will be what? That will be S1 dash. Okay, it will be S2 dash. This will be S3 dash and S4 dash. So now one more, what is going to happen? Wavefront is going to develop in the same similar manner, right? Like this. Okay, one more this thing wavefront is going to develop. So this will be what now? The dash S1 dash S2 dash. This will be what? This will be the secondary. These are what? The secondary wavelets. Okay, and this will be what? This will be the secondary wavefront. This will be the secondary wavefront. So in this way, he said that the light is going to propagate further, and so on. It is going to propagate, right? So there is one more thing which is important here is about the wave velocity. Okay, that is also important. So wave velocity in the wavefront, how it is the wave, this propagation is going to travel with some speed. That means the formation of the primary and the secondary wavelets, in between them, there must be some time lag. Let us see that time lag is supposed tau. So the time lag tau will remain the same, dear students, in formation of every wavefront. That means the next wavefront is formed, the same time is going to be taken. So this time lags will be same in formation of each and every wavelets one by one, right? Wavefront one by one. So let us understand now. The next one is what? Okay, this uh, calculation of this velocity, how I will do. Let us see that this, I am considering this as what? One of the wavefronts here, right? Okay, S1, S2, S3, S4, S5, these are the primary wavelets. So this will form one wavefront like this. Then again, what is going to happen? The next wavefront will be formed, right? After this, S1 dash, S2 dash, S3 dash, S4 dash, then S5 dash. Okay, new wavefront is formed again, right? And then again, what is going to happen? This will form one more new wavefront, right? S1 double dash, S2 double dash, then S3 double dash, S4 double dash, and S5 double dash. Okay, so this will form once more newer sort of a wavefront here. So now when the wave starts from this point to this point, S1 to S1 to S1 dash, it takes tau time. Then again, from traveling from S1 dash to S2 dash, right? Because the wave is continuously traveling in the form of the wavefronts, right? This is traveling. So again, from the S1 dash position to S2 dash, this time interval or the time lag will be also tau, right? Okay. Now your wave velocity will be what? Let's say your velocity in the same medium, it will be same. If the medium is changing, then what is going to happen? The velocity will differ. Otherwise, not. Let's say the medium is same, then the velocity will remain the same in all the particular wavefronts. The velocity of the light will remain the same. But if the medium is changing, let's say the medium is changing, suppose, right? Okay, when the different mediums are there, then what is going to happen? That this wave velocity will change, but this time lag will remain the same. That is very, very important. Okay, this is the most important theory. that this time lag will remain the same, but the wave velocity may change. That means your displacement vector can change. Okay, what will be the next displacement here, dear students? Suppose I just name this as these are the displacements here. Okay, so what will be the displacement? Delta x1 will be simply v times of tau. Similarly, delta x2 will be also v times of tau, and so on, because these are velocity and the time lag both are same. In case it is different, then these results will be delta x1, delta x2, and all these results will be different. So this is very important for the competitive exam. Even in the IITs also, this is being asked about the similar time lags and the wave velocities theory, right? Which I have explained right now. So students, the next one is what in the similar manner as we have learned the propagation of light, you can see in the Huygens wave theory, I have explained you the complete propagation of the light, that how is light is traveling, right, in the form of the wavelets, okay, and by forming the newer wavefronts and so on. Now comes what, that this Huygens wave theory can also be the one of the wonderful theories to explain the laws of the refraction. Okay, so I'm going to draw the diagram in the today's class, okay, that how do it is taking place, and then we are going to prove the laws of refraction using the Huygens wave theory. Even you can prove the laws of reflection also. That means all the laws of the ray optics can be validated, right, using the Huygens wave theory. So let us consider one what these. I'm just drawing one datum line here, right, and this one in the bottom is a denser media, right, and the above one, it is what, that is a rarer medium above this line, right. So I have got one incidented wavefront with me in on this rarer wave medium. This one is the incident wave medium here, incidented wavefront. A linear wavefront is there. This AB is a linear wavefront here. So this is the incidented wavefront. So I am going to draw one wavelet here like this, and the other wavelet at the point B, right, like this. Okay. However, I can draw many ones, but I'm just drawing these two, right. Now, what is going to happen, that you already know that whenever the light rays goes from rarer medium to the denser medium, it always shifts towards the normal. That is a simple theory of refraction. So I just draw the normal here first. This is the required normal, dear students, right. This angle is the angle of the incidence, right. Okay, because your this one will is what, this is the incidented ray, right. Okay, and this is the this one, this complete AB is what, this one is the incidented wavefront. Okay, incidented wave front. And the B is what here, this B is also the incidented ray, right. Okay, B will be also incidented ray. All right, this is also the incidented ray, right. So now I'm going to take what, I'm just going to draw the reflected ray here. The just normal I will extend. Okay, that means the reflected ray here will be how I will draw. Let us see that. Okay, the because the this ray will, whenever it will strike the normal, okay, and enter to the different media, that is a denser media, it will shift towards the normal like this. Okay, let me redraw this again. Okay, so it is going to shift towards the normal, right, like this. It is going to shift. Okay, so this one is what, this one is the angle of refraction. Okay, let me just tilt it a little bit so that you can watch very clearly. Yes, I'm going to just tilt it because there must be slight deflection here, like this. Okay, yeah, now it is fine. So this is the angle of refraction here. So it is also going to form the secondary wavelet. Let's say the secondary wavelet is A dash here. Okay, so this here I am going to draw here one wavelet. So this is one what was, this is what, very important. Okay, what is this? This is the A dash is the secondary wavelet, dear students. Okay, this is the secondary wavelet. Okay, so now this I extend as it is like this up to this point. Let's say this point is point C, and I just join this part of, okay, AC with A dash C with this only. This is not a rectangle, dear students. Okay, please don't get confused. This is not a rectangle, right? So here one incidented wavefront, secondary wavefront I have drawn. Other one I have not drawn. This is I've kept as C only. So now let us apply the Huygens wave principle here. Suppose in the rarer medium the speed of light is c1, and in the denser media the speed of light is c2. So the relative displacements, that is what, that is BC will be what, the time lag will be same. That is the important one of the Huygens wave theory that we are going to apply here, and that will give us the every result. So BC will be what, that will be delta x1. Okay, this will be what, in the rarer media the displacement will be what, that will be c1 times of tau. Okay, tau is a time lag. Now similarly a dash also you can calculate. So a dash is the speed of light in the medium denser media is c2. So delta x2, that is a dash, will be what, that is c2 times of tau, right? Both the values I've got, right? Now applying the principle here, right? Okay, that is the principle of the laws of the refraction. Okay, I'm going to prove simple principle of the trigonometry. Okay, the laws of reflection can be proved. We had to prove using this diagram. Okay, that we will do in the next class. The Snell's law I had to prove here, right? Okay, and what is basically the Snell's law, dear students? That is the sine of the angle of incidence by sine of the angle of refraction. Okay, that will be equal to what? That will, in this case, the refractive index of the denser media, let's say it is n2, and the refractive index of the rarer media is n1. So the result will be what? It will be n2 by n1. This result I had to prove using this principle. Very, very important, okay, one, right? So I hope that you have understood this two, three things which are very, very important, and this diagram also. Here is the, I can write here, this is the, this one will form the, here the refracted wavefront, dear student. That also I can write with the A dash C. This is a refracted wavefront, right? A dash C, and the incidented wavefront is your AB, right? So Huygens theory is a very complete theory regarding the propagation of the light, dear students, right? Okay, most of the assumptions of the Huygens are very much correct with regards to the ray optics. Okay, why? Because we are able to prove the laws of refraction using the Huygens wave theory in the ray optics particularly, right? Okay, that is why the most of the theoretical things, assumptions of the Huygens were correct. Okay, yet this phenomena of the wavefronts and all is very much restricted to the Huygens wave theory only, because there is no numerical proof of the same which is given by the Huygens in doing so, right? Okay, whatever I have explained you in this particular theory, okay, up to now. However, we are going to prove these results in the next class about the Snell's law and all, and the Huygens wave theory. Little bit we are going to discuss, but no numerical will be asked from this topic particularly. In the board exams, they don't ask you numerical, but on the contrary, they ask the question that you can state the Huygens wave theory, state the principle of wavefronts as I've taught you. Okay, all the three wavefronts you had to draw. I've explained you. You can see that. Okay, all the three types of wavefront I've explained you. That is what, that is the simply the spherical wavefront first, then the cylindrical wavefront I've explained you, and then the planar wavefront I've explained you. All these three type of wavefronts. Then the theory of wavelets you have to write. Okay, then after that you have to write the propagation theory of light using the primary wavelets and the secondary wavelet principle, that you have to write in Huygens wave theory. And then about the time lag, which I've explained you, that when a light ray is going from one wavefront to the other wavefront, it forms. It may be in different media, same media, that is not the problem. The time lag, that is tau, will remain the same, okay, in the two medias. Velocity may change, so that means your displacement vector will also change, right? But again, I'm saying you that the numerical problem for this particular chapter is not asked actually. Not asked in the, not in this chapter. The Huygens wave theory they would ask. On the contrary, they ask you the numericals from the next topic, which we are also going to discuss in the next class along with this proof, and that is the phenomena of interference. That is the most important one for the ray optics. and that will be surely asked in the exams. Many numericals from this topic, that is the phenomena of the ray optic, the interference, are being asked. And for that, because there is the experimental proof of that phenomena, okay, and that was done by the scientist Young, right? Young's, there's an experiment that is known as Young's double slit experiment, which is also there in the syllabus. The interference phenomena is very, very important, and most of the numericals which they ask from the wave optics, particularly they are based on the YDS only. Now this year, one important thing CBSE has done for you, that in this chapter the deleted portion is the polarization, entire polarization topic, which was very, very important. Last, up to last year it was there. This year they have removed in their 30% syllabus when they have subtracted, so they have removed this polarization topic, right? So that means you have to study only up to the single slit diffraction. Again, there are two topics which were there. That is, one is the resolving power of the microscope and resolving power of the telescope. That is also removed by CBSE. That means you can say 25% of this chapter, almost 25 to 30% of this chapter is being removed by CBSE. Okay, as far as the wave optics is concerned, right? Okay, so next we are going to start in the next class one thing, that is what, that is, we are going to start with the this proof of this Snell's law using the Huygens wave theory, number one, and then we are going to introduce the interference to you, and also maybe some part of numerical portion also with the proof, okay, we can do in the next class itself, right? Thank you so much, dear students. Myself, Professor Jitesh Jain here from the mytutorsonline.org. Okay, and I hope that you like this lecture, dear students, right? And please try to learn these Huygens wave theory. It's a very important one for exam. Why? Because even in the theoretical question, they can ask from 3 marks to 5 marks in the board exams, particularly. Also, in the competitive exams, the and assertion reason type of questions are being framed using the Huygens wave theory, dear students. So, thank you, everybody. Let's meet in the next class now. Bye bye for now. And next, we will study the interference, dear students. Thank you.